You've got a laser pointer.
Okay, so we've gone over RNNs and LSTMs, and we've also gone over LLM fine-tuning, but we haven't gotten into what we can say the core model architecture that's behind things like ChatGPT, or basically any LLM that's used nowadays, and many more models on top of that. So we've got transformers, yay! They're basically in everything or almost any model that you would be interacting with nowadays. That includes a lot of image generation models and a lot of computer vision models. And of course, language generation. So let's get into it. So what we've seen so far with RNNs and LSTMs is that RNNs are fairly good at processing sequential data, right? But they often fall victim to the vanishing gradient problem, which makes them unable to prioritize which information to keep. And that makes them, one, forgetful, and two, less effective. And LSTM solved that problem by being able to essentially more selectively remember and prioritize information. But they're still not that great at very long form data with context. So how can we improve upon this? So yeah, as I just said, LSTMs and RNNs can't process very long text inputs, or not that well at least, which makes them pretty ineffective for generating actually coherent text. So we want to do better. We need something that can process context effectively. So how do we get there? We have a phrase, the cat sat on the mat. If you put that into a model, or I guess you are the model, how would you determine which words are the most important and which words aren't important? I don't know. Raise your hands if you think you know what an important word is there. Yeah. Yeah. So cat is an important one. I mean, it's fairly simple. The words the probably doesn't contribute much meaning to the sentence, but maybe the verb sat contributes meaning, or cat, or mat, right? Or the preposition on provides a little bit of information. So here, this is just an example of, or a visualization of what might be prioritized. The cat sat on the mat. So you can see that the cat and the mat are the most important words because they give a lot more meaning to the sentence. But you can see that the preposition on is not so important, and the words the are the least important here. So this is what we would want our model to do, be able to essentially identify what is important and what isn't, which LSTMs and RNNs cannot really do. So what we want is each word to have its own attention weight. We want a model to pay attention to what's important. So how do we do that? Self-attention. So what we do is we have a sentence. Let's say I bought property in Egypt, right? Each token or word, well, we have a token called Egypt, and a token is essentially just a word. You can think of word and token as interchangeable. It's a little bit more nuanced than that, but that's basically how it is. But each token in self-attention can access each previous token. So Egypt can access in and property and bought and I. And what this does is that it helps a model learn which previous words contribute the most meaning to the next word and how each word relates to each other. By doing this, a model is more able to learn how meaning relates these words to each other. So this is the key idea behind transformers, and this is what we want. We want a model to be able to relate meaning between words in order to prioritize what words are important and which are not. So what we need to start with is QKV. So a query is what we're looking for, right? And what we can say for text data is the query is the location where we're at in the sentence. Next, we have the key. So the key in this case would be all of the past data or all of the past words that provide context to what we want to predict, which is the next word. And the value that we want is the information that we want. So the value in this case would be the predicted word. So the query then is where we're at. The key is all the past data, and the value is what we're trying to get. So I made a block diagram, a little block diagram that shows what we want. So we take the query and the key, and we put them, we process them using attention, and we get a value. And using this value, we can get an output. So, for example, with the sentence, I bought a property in Egypt, then we can say that the query is where we're at in the sentence, which is here. It's a blank space. And the key is all of this. I bought a property, and Egypt is our value, probably. Or I bought a property in Spain, or I bought a property in Los Angeles. It's hard to tell, but we can at least reasonably or more reasonably predict based on using a key or query key and value what we might say. So this is the core of self-attention, being able to use a query, key, and value to be able to, from context, predict what the next word or next token is. So this leads to naturally to transformers. So what we have here, or this is the actual block diagram from the paper Attention is All You Need, which introduces the transformer model architecture. But this makes no sense. So how can we break this down? Well, we can start with the encoder and decoder. And basically what the encoder does is it converts input sequences to numbers. So when we have an input sequence, like I bought a property or something, a computer does represent it in numbers. But we need to represent numbers, or we need to represent data in a way that is useful to do operations on. So we would probably turn them into vectors because we can more easily do linear algebra on that. And when we can do linear algebra, we can do a lot of things. And when we have a decoder, the decoder decodes it. So we just take the numerical sequence and we convert it back into words that make sense for humans. So words to numbers. We have a sentence, I bought a property in Egypt, and we can put it in our model. But not really, because this doesn't really make sense. We don't have a way yet to represent it numerically so that we can do operations on it. A model cannot do operations on just letters and words. That would be impossible, or at least it wouldn't be very useful. So what do? We want to take each word and convert it into a one-dimensional vector, right? So it's just a string of numbers. And we take each word and we represent it numerically. This is pretty arbitrary, but we want each word at least to be represented by a 1D vector. So I said, okay, each word can be a vector and it has 2 entries, right? And these are what we call vector embeddings. And this is how we represent tokens or words to be able to feed them into a transformer model. So this can be put in a model because these are numbers that we can do linear algebra on. So instead of words, we now have a way to convert words into something that's useful for us, or for the model at least. So when we can have 2 sentences that have the same, or essentially the same vector embeddings, right? I bought a property in Egypt and Egypt bought property in I. If you take what I did last slide, you would notice that we have the exact same vectors. It's just a bag of vectors. So we have the exact same words and the same vector embeddings. But if you're a human and read these two sentences, you can tell that these sentences have different meaning. So this is bad because what we've done so far is try to convert it into numbers that a model can process. But our model won't be able to process these two differently. It'll think they're the exact same. So we need to think of a way to prevent that from happening. So what we have now to solve it is positional embedding. So all we need to do is add a value to each token that represents a word's position in the sentence. So transformers process words all at once. So it processes every single word. Like if you have the sentence, I bought a property, it takes every single word at once. And we need to make order matter. So I can ask, does Eric wore a hat and a hat wore Eric mean the same thing? Obviously, no. So what will we do? Here, what I did is I decided to put positional embeddings here. So we add 1, 1, 2, 2, 3, 3, 4, 4, and 5, 5 here. So Egypt bought a property in I. This is a meaningful sentence, fairly or relatively meaningful. And if we attach 1, 2, 3, 4, 5 to each position, then it makes more sense. So then it's a distinct sentence compared to I bought a property in Egypt. So this is good because we achieved what we wanted to do, which is be able to differentiate two sentences that have the same words, but different meaning. So we can, and what's better is that we can feed all of these numbers into a model, and the model can actually do operations on it and thereby predict more text off of it, which is what we wanted. So, yeah. So let's take the sentence again. I bought property in Egypt. Originally, we tried to feed the sentence into the model directly. This didn't work. But when we try again, we try to tokenize it. So we turn each word and vectorize it into something that we can do operations on, or the model can at least. So we take I bought property in Egypt and we vectorize it. Then we add positional encodings. So this is very, very useful for us, as I said, because we can do operations on it. With training, or in order to train a model to do this, we have to make it know what to predict. So in our case, our value that we want to predict is the next token. And this is why tokens are useful for us, because you won't always want it to predict the next word necessarily, because tokens also can represent prefixes and suffixes as well, which alter the meaning of the sentence. But we want it to predict each next token, and we feed the model what we want it to predict. And then we apply dropout in attention layers and hidden layers. So basically what that means is knock out some neurons and try to make the model more robust. And the attention layers are just applying attention to the strings of tokens that we have, and the hidden layers are just processing the data as you would in a regular neural network. And label smoothing prevents the model from being overly confident. Yeah. So these are the pros and cons of transformers. A pro is parallel processing. So unlike LSTMs and RNNs, transformers are better able to essentially process more tokens at once, which makes them a bit better at, or they're better at processing information. great for long sequential tasks as they can use context. And to this day, they're used for state-of-the-art tasks. So if you go to Papers with Code or something and look up a lot of subtasks, you'll probably find that many tasks are using some sort of transformer architecture or something. And you'll also find that a lot of state-of-the-art models like DALL-E or AlphaFold or ChatGPT or whatever are using some variant of transformers. Now, nowadays there are a lot of different types of transformer models, but they all derive from this core idea or concept using attention and self-attention and query key value in order to deduce context. However, the cost of transformers is that they have a high memory cost because in order to process all that information, you need to compare what you want against everything else that came before it. So you need to be able to store a lot of data. And they're more complex to implement, and because as a whole, transformers are more complex than artificial neural networks or LSTMs, for example. But there are libraries, a lot of libraries out there that make the process a bit smoother now. So let's look back at this. This didn't really make any sense. But now we take attention, we have the attention, and we just put the information through it. Next, we have a neural network that processes the data and is able to essentially calculate loss when we're training it. Then we turn the words into vectors in order to feed into the model. And then as the output, we turn the vectors into words again so that they actually make sense. And now we have a useful model that can turn words that we input into it into words that make sense to us. So this is what happens when you input a query into ChatGPT. You ask it something or you tell it to do something, and from there it basically auto completes in order to fulfill your request. Yeah, and yeah, here there's where the word is in the sentence. So from here we have a completed block diagram where we have words. We have where the word is in the sentence, which is very meaningful to us. Then we have attention layers that we essentially use to figure out what is meaningful and what isn't. And then we feed it into a neural network, and then we decode the vectors we have into meaningful words. And that's about it. So why do we care about transformers? They're basically everywhere. As I said, basically any LLM that uses a transformer. So ChatGPT, Claude, Bard, whatever. Translation, Google Translate uses transformers in order to decode meaning in inputs. Image classification models and image generation models like DALL-E or basically any vision transformer uses transformers. And almost everywhere else in ML nowadays or deep learning research nowadays, because transformers are considered the chief paradigm right now in delivering results. Yeah, that's about it. So thank you. Are there any questions?
Your thought was
shorter meeting. Thank you everyone for coming. If you're not on the Discord or the Instagram, please go ahead and join so you can find out about more of these meetings as they come up. We have them this quarter every week. We're going to have another Wednesday 4 p.m. next week, and then Wednesday 4 p.m. the following week. It's week 7, and then finally on Wednesday 4 p.m. of week 10, we're going to have another we're gonna have a non-standard meeting where we're going to see the results of the competition, which is a competition that we hold every quarter. And basically, we ask you to create a neural network from scratch. And on week 10, we have people come by and present their projects and what they did and how they did. And you can earn some if you win, and just come by and see what other people did. Yeah, what's up? When are the projects due? Great question, Anthony. When are the Sky's No Limit projects due? March 2nd. And is that 11:59 p.m.? 11:59 p.m. March 2nd is when the projects are due. Yeah, we'll be here for a little while, at least, setting up the video and stuff like that. If you have any further questions about Transformers, that was kind of high level. We'll be here to answer them, or et cetera, if you have any questions in general. But yeah, have a great day, and we'll see you guys next week or around. Thank you so much.